All right, today we're going to do something cool. We're going to make the invisible visible. We're talking about the world of gases, the simple rules they follow, and get this, how chemists actually count their impossibly tiny particles.
I mean, it seems like magic, right? A huge balloon just floating there. But nope, it's not magic at all. It's just physics. The secret is all in that invisible world of gases, which, as it turns out, play by a very specific and surprisingly predictable set of rules. Okay, so to really get how gases work and, why that balloon floats, we've got to start with the basics. We need to get a handle on three key things we can actually measure. We're talking about their volume, their pressure, and their temperature. So let's break these down. The really unique thing about a gas, it's all about its volume. See, unlike a solid or a liquid, a gas has no fixed shape at all. You can put 1 liter of air into a 10-liter container, and poof, it just expands to fill up the whole thing. And this one simple idea, well, it's the key to understanding everything else that follows.
So back in the 17th century, scientists started noticing something really interesting. They realized these three things, pressure, volume, and temperature, they aren't just separate properties. Nope, they're all connected in this really elegant way, through a series of laws.
All right, let's dive in with the first big one, discovered by a guy named Robert Boyle. It's probably the most famous. What he found was, as long as you keep the temperature the same, there's this super simple relationship. If you squeeze a gas, crank up the pressure, its volume gets smaller. And if you give it more space, its volume gets bigger. Simple as that. Just think about a bicycle pump. It's a perfect example. When you push that handle down, what are you doing? You're increasing the pressure on the air inside. That forces its volume to shrink right down until it has no choice but to rush into your tire. Then you pull the handle back out, and the exact opposite happens. It's this perfect inverse relationship. Okay, next up we have Jacques Charles. He was curious about the link between volume and temperature. And what he found was a direct relationship. You heat a gas, it expands. You cool it down, it contracts. And, fun fact, the law specifically uses the Kelvin temperature scale. Why? Because Kelvin starts at absolute zero, which makes the math behind this relationship just, perfect. And this explains something you've probably seen 100 times. You know when a balloon looks kind of sad and deflated when you take it outside on a cold day, but then you bring it back inside and it plumps right back up? Well, that's just Charles' law in action. The little gas particles inside are just following the rules. They slow way down and huddle together in the cold, and then they speed up and spread out again in the warmth. So, here's the really crucial part. These laws, they aren't just some abstract rules from a textbook. No way. They're the direct result of what trillions and trillions of tiny, invisible particles are doing, like right now. This was the huge breakthrough, connecting the big stuff we can see with the tiny stuff we can't. This is what's called the Kinetic Molecular Theory, and it's the why behind everything we've just talked about. It tells us that pressure, it's really just the combined force of all those zillions of particles smashing into the walls of their container. So if you squeeze them into a smaller space, well, they're going to hit the walls more often, and boom, pressure goes up. That's Boyle's law. And temperature, that's just how fast those particles are zipping around. So if you heat them up, they move faster, they hit the walls harder, and they push those walls outward, making the volume bigger. And that is Charles's law. Okay, but wait, if everything is about what these individual particles are doing, that brings up a huge problem, especially for chemists, right? Because to make a chemical reaction happen, you need the exact right number of particles. So how on earth are you supposed to count them? I mean, you can't just count them, 1, 2, 3. It's literally impossible. A single drop of water has more molecules in it than you could count in 1 trillion lifetimes. No joke. So chemists had to come up with a much, much cleverer solution. What they did was they invented a special counting unit. It's really no different than how we use the word dozen to mean 12 or pair to mean 2. Chemists use the word mole, and all mole means is a specific and very, very large number of particles. It's just a convenient name for a giant quantity. So you're probably asking, okay, so how big is this quantity? Well, 1 mole of anything, whether it's atoms, molecules, whatever, is 6.022 times 10 to the 23rd power of them. It's an absolutely massive number, and it has a name, Avogadro's number, named after the scientist Amedeo Avogadro. Just look at that number. That's Avogadro's number written out. It's 602 sextillion. It is so mind-bogglingly huge that if you had a mole of basketballs, you could create a new planet the size of Earth. Seriously. And yet, that's how many atoms are in just 12 grams of carbon. This concept, this number, it's basically the cornerstone of all modern chemistry.
So, okay, it's a giant number, but how is it actually useful? Well, let's take a look at how this one idea, the mole, becomes the essential tool that lets chemists precisely build, well, everything, from medicine to new materials. The best way to think about it is like this. Using the mole is like using a measuring cup when you're baking. Chemical reactions are really just recipes, and the mole is what lets chemists measure out the exact right amount of their atomic ingredients to get the final product they're looking for. Let's take ammonia, for example. It's a super important ingredient in fertilizer. The recipe for it is always the same. You have to combine 1 mole of nitrogen molecules with 3 moles of hydrogen molecules. You follow that recipe, and you will get exactly 2 moles of ammonia. It's this level of precision that makes all of our large-scale chemical manufacturing possible today. So when you think about it, from the simple, elegant laws that explain why a hot air balloon rises, all the way to this incredible concept of the mole that lets us build complex medicines from scratch, these ideas are quite literally the building blocks of our modern world. And it really makes you wonder, doesn't it? What are we going to build with them next?